Let's build up a simple circuit using some logic gates. Now this is called a flip-flop or latch. And in this case it is a very simple flip-flop with a set and reset. That's what the S and R represent. Our output is labeled Q. And as you'll see, that's usually the case with flip-flops. I have no idea why they called it Q. But hey, if you got to pick a letter of the alphabet, might as well use one that hasn't been used yet. All right, notice that we have provided feedback from our output to our first gate. Now this creates an unusual holding effect that we can use to our advantage. Let's walk through what happens here. First, we fire up our circuit. We have lows on both the set and reset inputs. Now we just turned the power on, so there will be a 0 on the input here as well. As an OR gate, if either the first input or the second are high, the output will go high. Neither are high, so the output will go low. However, it is inverted. It is a NOR gate, so the output will go high. Our second gate, as an OR gate, will go high if either the first or second inputs are high, which we now have. We have a high on our first input, so the OR gate will want to go high. However, it is also inverted. It is a NOR gate, so its output will go low. This feeds back low to the first input on our first gate. We now have two lows on our first gate, holding that output locked high. A funny thing happens when we put a high on the set input. This is a NOR gate, and we now have a high on one of the inputs. That means the output will go low because it is an inverted OR gate. Now, because we have a low on both inputs of our last NOR gate, the output goes high on Q because it is inverted. We have just set the output high. Now watch what happens when you remove the high from the set input. Because the feedback line is high, it holds the output of the first NOR gate low. We have a low on the reset line, and so the output stays high. It holds it high. It locks it in. It latches the output. This is why it is commonly called a latch. No matter what I do to the set input, the output is now latched high. However, when I put a high on the reset line, there is now a high on one of the inputs of the last NOR gate. That triggers Q to go low, which feeds back to the first NOR gate, which now has a low on both inputs. The output of that NOR gate will now go high, and no matter what I do with the reset input, Q will stay low because of the feedback. So as you can see, we can use a flip-flop to store one bit of data. As long as power is applied to the circuit, it will hold whatever value we last stored there indefinitely. We can also do this with NAND gates, of which we have a quad NAND gate chip in your kit. If we set it up like this, it does the same thing as our previous flip-flop. However, it is set and reset with an active low signals. So in other words, a low on the set input triggers Q to go high. Now this is certainly still useful. This is called an SR flip-flop or a set-reset flip-flop. And while useful, it is more practical to us to have an active high set the flip-flop. No problem, we can run the inputs through NOT gates and invert the signals. You'll also remember we could build NOT gates out of NAND gates by simply tying the inputs together. So here's an SR flip-flop you can build using your 4011 chip. With flip-flops, you'll see a lot of common pin names, and you can actually buy pre-built flip-flops on microchips, and you'll see them in schematics represented like this. There are two outputs, Q and not Q. So you'll often see this horizontal line above digital labels, and this usually means it's inverted. In the case of our flip-flop, it means it is the opposite of the Q output. If Q is high, not Q is low. If Q is low, not Q is high, always. This happens because the outputs of the last two NAND gates are cross-linked. If you want, you can build this circuit. The schematic is in the downloads. There is one problem with this flip-flop. Set and reset cannot both be high at the same time. This actually induces instability into the circuit. It turns the circuit into an oscillator, really, and so you have no idea what the state of the flip-flop will be when one of the inputs goes low. So set and reset being high at the same time is disallowed. Now obviously this greatly limits the circuitry, but we'll get back to this in a moment. These flip-flops are what we call asynchronous. They are not synchronized in any way with any other circuit. They will act and react immediately when we either send a set or reset signal. Let's build a more complex synchronous flip-flop, see what that is and why we want it. In the download section, you'll find the schematic diagram of the circuit we're going to build. We are going to build what is called a D-type flip-flop. There are a number of flip-flops out there. We've already seen the SR flip-flop, which requires two separate control signals. If we wanted to store more than one bit of information, we couldn't really synchronize it, so it will only store the signal at a specific time. With D-type flip-flops, we can control when the flip-flop stores the data with the clock input. So we're going to build up a D-type flip-flop using logic gates. The schematic is in the downloads section. This feedback line from the output of the set NAND gate to the input of the reset NAND gate ensures that the set and reset are never high at the same time. The clock input causes the flip-flop to be set to whatever the set input is, whether it be high or low. So here we can see the circuit in action. I've got the right push button wired up as the clock signal and the left button wired to positive with a pull-down resistor. So when I push the button, it puts a high on the set input. And if the button is released, set sees a low signal. So whenever the clock signal goes high, the flip-flop stores whatever the signal is at the set input. If set is high and I push and release the clock, it stores the high on the output. Nothing I do after that will change the output. If set input sees a low when the clock pulse goes high, then boom, it stores the low it sees on the set input. Nothing I do on the set input changes that. Now you might be wondering, who on earth cares? Well, congratulations, you just made a computer memory. Now it's only 1 bit. If you made 8 of these and put them in parallel with their clock lines all hooked together, you could store a byte. It would be a 1-byte memory bank. Now consider this. Remember the transistor-transistor logic that goes into a NAND gate? Now expand that to 4 NAND gates. Now expand that to 8 banks of D flip-flops. Now the memory sticks on your computer might have, say, 8 gigabytes of memory. That's 8 billion of these banks of 8D flip-flops. This starts to give you an idea of just how many microscopic transistors are just in your computer's, desktop computer's memory sticks. So I will call these flip-flops, these latches, I will call them registers. They register a digital value. These registers can act like memory and store a digital bit. The output can be read, or the output can be used to turn on or off certain electronic circuitry. So in other words, I can send a digital 1 to this register, and the output actually turns on an electronic circuit which, I don't know, turns on a relay which powers a motor. As long as that register shows a 1, the motor is powered. I can then send a 0 to the register and turn it off. So I can read the state of the controlled circuit by simply assuming that if I read a 1 there, the controlled circuit is activated. If it's 0, the controlled circuit is turned off. We will use registers and memory extensively in digital electronics. Now, one quick clarification before we go on. If we are using these registers as memory to store a digital number, the moment we remove power from that circuit, we lose that number. The chips all reset and turn off because there's no more power. We call this volatile memory. Because we can write and read the register, we call this memory random access memory, or RAM for short, because we randomly access it for storing the number or reading the number from the register. Now, RAM is fast, but vulnerable to power loss. Read-only memory, or ROM, is a bank of memory that cannot be written to. It can only be read. Now, often this is literally hardwiring on a microchip. A bank of 8 wires makes up a byte of memory. Each bit has a connection to positive or a connection to negative. The advantage, of course, being it is non-volatile. That is, you have the numbers stored in memory even when the power goes out. There is also electrically programmable read-only memory, or EEPROM for short. This is literally memory which is written by burning microscopic fuses in banks. You'll have a byte of fuses which connect to positive. When you program the chip, you apply enough voltage and current to the bits in the byte that you want to set high, and it burns off the fuse. There is now a pull-up resistor pulling the voltage at that bit high, but you can only write to it once. Then there is electrically erasable programmable read-only memory, or EEPROM for short. A simple way to think of this is capacitors store a charge which represents a 1 or a 0. You program the memory by applying a high to the capacitors, which store a voltage. The data is preserved even when the power goes out because it is storing a charge and thus not relying on the power. But capacitors take time to charge up or discharge when you send a 0. So EEPROM is typically much slower to write than RAM. But the advantage being the memory is non-volatile. Now, I've simplified it for the sake of learning. Capacitors do leak, and so they discharge over time. So EEPROMs often have things like recharge circuitry, which goes around the entire memory bank, reading each memory location and recharging the ones to preserve the memory. Flash memory, like what you have in the common thumb drive, would fall under the EEPROM category, but it's even more complex in how it functions and stores a charge in each bit. But you can think of it as effectively a capacitor storing a charge. It's slow writing to it compared to RAM, and you can write to RAM an infinite number of times. Flash memory has a life. You can only write to it so many times. Every time you write to it, that charging of the memory locations wears it down to the point where the memory bits will no longer hold a charge. Now, this number of writes can be anywhere from 1,000 to 100,000 or more times. Now, yes, that's a big number, but consider that your desktop computer writes to its RAM sticks millions of times per second. How long do you think your flash memory would last? Now, we'll get into that in even more detail later on, as we will use microcontrollers which have flash memory on board that you can use to store data that is preserved even when the power is lost or turned off.